So with rational functions, they're functions that are fractions where there is at least one x in the denominator. Okay, it has a whole definition here, blah, 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 we can read that, but really, you are looking at those inverse variation functions that we learned last class, where the x is in the denominator. That will make a rational function. Now we have the parent function for these rational functions. Just by looking at this graph, can you guys give me some description of what that blue graph looks like? Doesn't have to be math terms. Tell me what it kind of looks like.
Which one?
The blue graph, what does it kind of look like? Use some descriptive words.
Elbow.
Kind of like an elbow, but not just one elbow. How many? Two elbows. So we got this elbow and we got this elbow. I like to think of them as bowls. So you've got like two bowls, right? You got this bowl and you got this bowl. Okay? Here's the deal. This shape is technically called a hyperbola. Ew. But that's what it's called. It's like a parabola, but with the prefix hyper instead of para. So it's a hyperbola. It's two symmetrical parts called branches. I like to call them bowls, but we have two branches. And these two branches are separated by two lines that are invisible, but essentially exist on every single rational function. Right now, I want you to pick one of the color highlighters that you have. Designate that as the vertical line all day. That's going to be your vertical line. And I want you to take your highlighter and I want you to highlight what's called the vertical asymptote. Ooh, that word, vertical asymptote. Have y'all ever heard of an asymptote before? I really hope you have, because in Algebra 1, when you had exponential equations, they had a horizontal asymptote. Asymptotes are lines that are invisible, that your graph is going to get very, very close to, but it is never allowed to touch it. So we have what is called a vertical asymptote. I'm going to use the shorthand VA for vertical asymptote. Is that okay with everybody? A VA, or a vertical asymptote, is a vertical line that your graph is going to get very, very close to, but it is a boundary line. You are not allowed to touch it. So if you see your graph, as we get close to that vertical asymptote, it shoots off down to the bottom. And then when we pass the vertical asymptote, it comes from the top. That's a vertical asymptote. These graphs also have a boundary line going up and down called a horizontal asymptote. So choose your other color and I want you to highlight. It is the x-axis yet, but it is the line x equal to 0. That is called your horizontal asymptote. Horizontal is a flat line, and the asymptote is a line that the graph is going to get close to but never touch. So we have two boundary lines on this graph that kind of chop it in half. These two lines create the two bowls because we're not allowed to touch or cross them. So all of your graph is entirely contained on one or in two of the four quadrants. Ooh, the quadrants. Let's talk about those again. What quadrant is this? It is quadrant 1. So let's label that as quadrant 1. We use Roman numerals for the quadrants, which is why it looks like an I. That's the number 1 in Roman numerals. What quadrant is this one? 2. So we're going to put quadrant 2 over here. If I go down, what's the next quadrant? 3. Again, Roman numerals, so it's the Roman numeral 3. And then the last quadrant is quadrant what? 4. To write 4 in Roman numerals, you do 1 and then a V, or an I and then a V. So if we look right now, your parent function is contained entirely in which two quadrants? 1 and 3, because of the boundary lines of your vertical and your horizontal asymptote. It is contained entirely in only 2 of the quadrants. Now, because we have these boundary lines that create the two different branches or bowls, I'm going to keep calling them bowls, even though I know your paper says branches. That's the more correct name, but I like bowls. We have what are called a specific domain and range that exclude a certain number. Our domain is going to be represented by this notation. x such that x is not equal to 0, which is a really fancy way to say all real numbers but not 0. So literally everything but not 0. Because at 0, we have the vertical asymptote that's cutting our graph in half. So we can't include that. The vertical asymptote is something we can't touch. So we can't touch it in the domain, we can't touch it on the graph. Your range is the same thing except that the letter changes to y because range is y. So that notation, y such that y not 0, is a fancy way of saying all real numbers but not 0. So your vertical and your horizontal asymptote here are going to divide the graph into 4 quadrants, or 4 fake quadrants when we start moving it off the graph, which we'll talk about later. So our goal today is to be able to graph these functions and more specifically talk about their vertical and their horizontal asymptotes. We also are going to want to compare all of the graphs we do today to this parent function. Now, one thing that we want to be able to do, this horizontal asymptote is y equals 0, is remember the acronym HOI-VUX. Do y'all remember learning about the acronym HOI-VUX in Algebra 1? Yeah, I hope so, because some of you had me for your teacher in Algebra 1. When we do HOI-VUX, we used to write it like this, on purpose. HOI stands for what? What does the H in HOI stand for? Horizontal, which means the slope is, and the equation is going to start with y. That's the important part right there for us today. When we write our HOI equations, our horizontal asymptotes, the equation should always start with y equals. Don't pick an x equals, it should be y equals. But for our VUX lines, the ones that go up and down, what does the V stand for? Vertical. Ooh, do we remember the U? Undefined. Very good. Up and down lines have an undefined slope, and their equations start with what? X. If you can remember HOI-VUX, the y and the x, then you will not miss one of the questions that asks you to write the equation for the asymptotes. Because if it's vertical, it's x equals. If it's horizontal, it's y equals. That make sense? Okay.
What's the O?
It's a 0. Yeah, it's the slope is the middle letter, so in HOI it's 0, and in VUX it's undefined. Okay, so the kinds of questions you're going to see today are going to be like this, where we want to graph this function and compare it to the parent function. We are going to be graphing the line g of x equal to 4 divided by x. Go ahead and circle that right now. So to do this, we're going to plug some numbers into our table here to get some numbers out and be able to see what our transformed graph looks like. The numbers we're going to plug in are numbers 1, 2, and 4. And I chose these numbers specifically for a reason. When we plug in the number 1 into where x goes, we would just be doing 4 divided by 1. And what's 4 divided by 1? Oh my gosh, we're overthinking it. What's 4 divided by 1? 4. If we plug in 2, we'd have 4 divided by 2. And what's 4 divided by 2? And then the reason I skipped 3 is because 4 is not divisible by 3. If we plug in 4, what's 4 divided by 4? 1. This gives me a whole bunch of points that I can plug into my equation. That I can plot on my graph. We have these coordinate points. We have the coordinate point over 1 up 4. We have the coordinate point over 2 up 2. And we have the coordinate point over 4 up 1. Now, I know I've only given some points for this upper bowl. We'll get to the lower bowl in a second. When I play connect the dots here, there are a few more rules that I have to remember. Can I graph my line? Don't do this. Can I graph my line like this?
No.
Why not? Maybe 2 reasons. Number 1, that's a weird way to connect the dots. Number 2, aren't there boundary lines for this type of graph that I'm not allowed to cross or touch? So there are boundary lines that we're not allowed to cross. those boundaries are the same as the ones above, which means that there is a vertical asymptote at 0, and there is a horizontal asymptote at 0. Those are boundary lines that we're not allowed to cross whenever we graph our function, which means the only way I can play connect the dots and not cross those boundary lines is if I make it look something like this. Not touching the green one and not touching the purple one. Now, if we were to find the points for the other side and we plugged those in, they would look something like this. Okay, let's do the coordinate points -1, -2, -4. That means our values would be -4, -2, -1. So 1, -4, -2, -2, and -4, -1. So again, to abide by the rules, I have to not touch the purple line, but touch all the points, and then not touch the green line. And voila, we've graphed both branches, or both bowls, for this hyperbola. Now, it does ask us to compare it to the parent function graph, so we need to do a couple comparisons. The first comparison we're going to write is about what quadrants they're in. Both the graphs, the one printed on your paper and the one we just graphed, what quadrants are they in? Both are in quadrants 1 and quadrant 3. We didn't do any sort of changing of the quadrants, so that's one thing we can compare it with. The second thing we can do is compare the domain and the range. But if we compare the domain and range, all we have to do is look at where the vertical asymptotes are. Did I change where the vertical asymptotes are from the parent function to the red graph?
No.
No, so my domain and range are going to be exactly the same. We're going to say that the domain is all x's such that x is simply not equal to the place where the vertical asymptote is. And what number is my vertical asymptote at? It's at x equal to 0. So since my vertical asymptote is at 0, then that's the number I have to pick out and throw away from my domain, because I can't touch 0. I can't touch it on the graph. I can't touch it on the domain. I can't plug it into the function. There's just no 0. And the same idea applies for the range. It's going to be all y values given y is not equal to whatever value the horizontal asymptote is at. And what value is my horizontal asymptote at? What level? Did I move it up or down? So it's still at 0. So that's the number I have to throw away out of my range. So the conclusion we draw here is that these two graphs have the same domain and range. The last conclusion we're going to draw here is about the distance from the axes, axi. So would you say that g of x, which is the red function, is it closer or farther from the axes from the one printed on your paper? Is the red graph farther or closer to the axes than the black graph? Farther. It's farther away, right? So it's farther from the axis than the original function f of x. Those are the three conclusions we can draw here. So things I want you to recognize here. When we are graphing these functions, you just plug some numbers in, right? You can use Desmos, you can use your calculator to find what the graph looks like, but when we're comparing it to the parent function, we need to know if it's changed quadrants, we need to know if the domain has changed, and we need to know if it's further from or closer to the axes. Those are the sort of conclusions we're going to draw. Yes? Can we do another example of one that's different? Great. Open up your packet. We're going to go on the inside here, and we're going to see one more example. So we're going to graph this time the g of x function such that g of x is negative 5 divided by x. And I'm going to change to blue just so it looks different. Just before we start, the last function was just 4 divided by x. This time the number has changed to what? Negative 5. First of all, when we make things negative, what does that mean for our functions? When we add a negative in front of a function, what does it normally do or transform our graph like? Opposite, sort of. I'm looking for a word that starts with an R. It reflects it. So we're pretty confident that we're going to have some sort of reflection here, just because we know that it's negative. We'll hold on to that idea while we work this problem. Okay, we need to plug in some numbers. The numbers we're going to plug in here are going to be 1, 2, and 5. 1 because it's easy to work with, 2 because it's easy to work with, and 5 because 5 is divisible by 5. If we do negative 5 divided by 1, we'd get negative 5. Negative 5 divided by 2 is negative 2.5, which, yes, I know that's a decimal, but that's a cute decimal. And then negative 5 divided by 5 is negative 1. If I graph those points, it's going to look like this. Over 1, down 5. Over 2, down 2.5. Do your best to graph 2.5. And over 5, down 1. Whoa. What quadrant did I just plot all of those points in? Quadrant 4. That's weird. We've never been in quadrant 4 before. And if I wanted to graph these lines, I have to know where my boundaries are, where the asymptotes are. My asymptotes are still going to be at 0 and at 0 because we haven't started transforming these graphs yet. So if I look at those boundary lines, the bull or the branch can only be in that 4th quadrant. We can't cross the green or the purple line. If we were to extend this table to include some negative values, we're just going to do the same negative values. Negative 1, negative 2, negative 5. And we plug that number in. Negative 5 divided by negative 1 is positive 5. Negative 5 divided by negative 2 is positive 2.5. And negative 5 divided by negative 5 is positive 1. Literally just the opposite signs. Which means my other coordinate points are negative 1, 5, negative 2, 2.5, and negative 5, 1. Whoa, that's in a different quadrant as well. And if I abide by the rules, which means don't touch the purple line, touch all the points, don't touch all the green line, this is what my graph might look like. Okay, let's draw some conclusions here. First things first, what's the equation of my vertical asymptote? X equals 0. Thank you for saying x equals. So x because it's vertical, 0 because that's the number it's crossing. What's the equation of my horizontal asymptote? It's horizontal, so it should start with what? It's a Hoy line, so it should start with what? Y. And what level is it at? 0. Okay. We didn't change that yet. And if we compare the two functions together, we're going to say that g of x, which is the blue function, is that reflection that Jamil noticed earlier into two different quadrants. This time it's in quadrant 2 and quadrant 4. That's a change. That's how we compare it. It's no longer in the same quadrants like the first example was, because we've flipped it. The second conclusion we're going to draw is about the domain. The domain, when I'm writing it, is going to be the squiggly bracket x such that x is not equal to 0. That's coming from my green vertical asymptote line. My range is y such that y is not equal to 0. Again, coming from my purple horizontal asymptote line. So the conclusion we draw is they still have the same domain and range, even though I flipped it, which is pretty cool. And then again, the last conclusion we draw is that it's harder to tell this way, but this is still having g of x be farther from the axes than f of x. Now, the reason I know this is because actually this number -5 created what was called a vertical stretch in my graph. And if you remember anything about vertical stretches versus vertical shrinks, stretches are going to stretch away from things and vertical shrinks are going to shrink towards things. And if you're like, I truly don't know, graph it. See if it's further or see if it's closer. So one of the conclusions we can draw after seeing these two examples is the following. If we have a positive graph, like we did on the front, the two quadrants that the graph is going to be in are going to be quadrants 1 and quadrant 3. But if we have a negative graph, meaning it has been reflected, like in the second example, which two quadrants is it actually going to be in?
1 and 3.
2 and 4. That's a great conclusion to draw from these two examples, that they're going to always be in the same quadrants until you reflect it. Then it switches quadrants because it's reflecting over that x-axis. Now, a question you might be asking, and maybe you don't care, but here's a question that might be interesting to you. What happens if the vertical and horizontal asymptote are not both at 0? Because that's possible. And that's the next question that we're going to talk about. That means that we have translated this graph, or we have moved the graph away from having the vertical and horizontal asymptote meet at 0, 0. So let's say we start translating this graph. I want everybody to circle, star, highlight, underline this equation right here. Y equal to a divided by x minus h, get out of it, plus k. Ooh, h and k. We've been talking about h and k's for a while. I want you to highlight the h with whatever color you've been using for your vertical lines. For me, it's been green. So your vertical line color. And then I want you to highlight the k with whatever color you've been using for your horizontal lines. And then if you wanted to keep doing these color schemes on the vertical asymptote and the horizontal asymptote, you can go ahead and color those two colors. I'll give you a second to make sure your color scheme is right. So the steps to draw graphs when we have moved them outside of the 0, 0 type asymptotes is as follows. We're going to draw the two asymptotes quickly. X equal to h and y equal to k. Those numbers come from the equation. However, do you notice that in the equation you see minus h, and then in the equation you just see a regular h? That means that we are going to use the opposite sign for h. But for k, you should use the exact same sign. And don't get those swapped. H, or your vertical asymptote, always comes from the denominator. Your horizontal asymptote always comes from the big number behind it. After we do step 1, we're going to plot points to the left and to the right of the vertical asymptote. And that step is going to come from this conclusion we drew. Whether your bowls are going to be in fake quadrant 1 or fake quadrant 3, or the opposites. And we're going to connect our dots. So what I mean by that is, let's see an example. Okay? Are we okay with seeing an example? I see some people still writing. Okay. Example 3. Now, first of all, if you don't like things to be blank on your notes, we're not going to use this, because we're just going to sketch this graph. The graph that we're going to sketch is f of x equal to negative 4 over x plus 2 minus 1. Immediately, I want you to take your color that represents your vertical asymptotes, and I want you to highlight the number plus 2. The reason we're highlighting the number plus 2 is because that means that my vertical asymptote is going to appear at x equal to, not plus 2, but minus 2. It's no longer 0 because we've started translating this graph around. So that means immediately I can draw my vertical line that my graph is never going to cross at negative 2. It's no longer at 0. We've shifted it over to the left at negative 2. Then I want you to take your highlighter color that you've been using for your horizontal asymptotes, and I want you to highlight the negative 1. We don't touch the stuff in the numerator. Not yet. That number right there is going to help me figure out what my horizontal asymptote is. But you don't change the number on this one. That means that my horizontal asymptote is at negative 1. So take your highlighter color and draw a horizontal line at negative 1. Those are your new boundaries. You cannot cross them. They also, for the idea that I want to use for graphing them, create fake new quadrants. I'm using air quotes here. This quadrant, I know this is the quadrant, but if we pretend like my vertical and horizontal asymptote create a new x and y axis, this is quadrant 1, this would be quadrant 2, this would be quadrant 3, and this would be quadrant 4. Now, because our graph is negative, did y'all notice the little negative right there? If this is negative, which two quadrants or fake quadrants should my bowls be in? Should my branches be in? Look at what we wrote down.
2 and 4.
2 and 4. Okay, but we're going to use the fake quadrants created by the intersection of my two asymptotes, which means I'm going to have a graph here, and I'm going to have a graph here on the 2 and 4 side of my vertical asymptote. Remember, your graph cannot touch the highlighted lines. It can get very close to it, but it can't touch or cross it. Obviously, we're human, so our drawing is not going to be as good as a computer, but that's what we're going to draw. And voila, we've graphed it. That would give us a good estimation to be able to choose the correct answer on our homework or on our tests. It should know what the graph should look like. The last thing we're going to do, though, is talk about the domain and the range. But these are really easy to write once you've found your vertical and horizontal asymptote. Because the domain we just write as all numbers such that x is not equal to what number? It used to say 0. This time it says negative 2. Very good. Where'd you get the negative 2 from? It's the number we highlighted. Very good. It's the same number here. We should use the same number for my vertical asymptote as the number that is not allowed in my domain. That's what a vertical asymptote is. We're not allowed to use it. Which also means that if I wanted to write my range, the range would be all y values such that y is not equal to what number? Negative 1, the number directly from where I've graphed the purple line, and which is my horizontal asymptote. We've just got one more example, but y'all are going to drive on this one, so you're going to help me fill everything about it out. So I'm going to scroll down to that one. Okay, we want to graph this new f of x function. Is this a negative graph or a positive graph? Positive. I don't see a negative in the very front, so I know it is positive, which means which two fake quadrants is it going to be in?
1 and 3.
1 and quadrant 3. Again, these are the fake ones created by my horizontal asymptote since we've translated the graph around.
So how do you know it's positive by the +5?
No, not because of the +5, but if you look at the two functions right here, the one on top has a negative in the very front. This one does not. Yeah. That negative can either be here up in the numerator or just like chilling out front. But as long as it is in front, that makes it negative. That was a great question. Okay, what number should I highlight in? I'm highlighting my vertical asymptotes in green. So what number should I highlight in green? -1, the number in the denominator. Now that means that my vertical asymptote appears at x equal to, not -1, 1. Okay, fabulous. +1, which means I'm going to draw my vertical asymptote, the invisible boundary line, at 1. Check. My horizontal asymptote is going to appear at what number? 5. Just the big number chilling by itself, not the number in the numerator. That does not affect my horizontal asymptote at all. I just want the number that's chilling by itself. Which means that I can then graph a horizontal line at 5 that's going to represent my boundary line. Now we have a big shift here. We've shifted it not just slightly off of the x and y axis, but a wild amount on the y axis. That's okay. You guys told me it was positive, so it should be in the top right and the bottom left quadrant. Quadrant 1 and quadrant 3. The ones created by that shift in the horizontal and vertical asymptotes. I know that it is not actually quadrant 1 and 3 because we've shifted it. But it's in the top right, bottom left quadrant. Hooray! All that's left is the domain. Help me write that. All day when I've been writing the domain, what have I started all of them with?
The squiggly thing.
The squiggly thing, great. And then what letter?
X.
X, and then that big old bar, and then what? X equal or not equal?
Not equal.
Not equal to 1. Where did the 1 come from? One more time. Where'd I get 1 from? All the numbers I've highlighted in green are the number 1. That's where the number 1 comes from. It's from my vertical asymptote. That's what we have to throw away. When I write the range, again, we started off with what? Squiggly bracket. What letter? Y. And then the bar, which means given or such that. And then what? Not equal to 5. Very good. It's the same number as my horizontal asymptote, the boundary line that's flat that I'm not allowed to cross or touch. So graphing these functions is a little weird at first because they're not a shape we're used to seeing. They're a shape we're like, oh no, we got it wrong because we typed an x in the denominator. Well, now we're doing that on purpose. The main gist of this is that you need to be able to figure out what the vertical and horizontal asymptote is very quickly. Those come from these two places, the denominator and then the big number by itself. Okay?